Everything we see, touch, and feel, from the glow of a candle to the beating of a human heart, is powered by energy. But what if energy isn't continuous, flowing like an endless stream, but instead comes in tiny, indivisible packets, quanta? This revolutionary idea, the quantization of energy, shattered the classical worldview and gave birth to quantum physics, the framework that defines modern science, technology, and our very understanding of reality. Today, we trace the story of how light and matter were revealed to dance in discrete steps, a cosmic rhythm written in quanta. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. At the dawn of the 20th century, physics seemed complete. Newton's mechanics and Maxwell's electromagnetism appeared to explain everything from falling apples to the glow of stars. But there was a problem, a deep one. When scientists tried to calculate how a blackbody, a perfect absorber and emitter of radiation, should radiate heat, classical physics predicted that as wavelengths shortened, the emitted energy would explode to infinity. This catastrophe was called the ultraviolet catastrophe. Enter Max Planck, a reserved German physicist working in Berlin in 1900. Planck was desperate to match theory with experiment, so he introduced what he called a mathematical trick. He proposed that energy could only be emitted or absorbed in discrete chunks, each proportional to the frequency of the radiation. That tiny constant, h, now known as Planck's constant, forever changed physics. It implied that nature, at its most fundamental level, is quantized. Energy exists in steps, not in a smooth continuum. Five years later, Albert Einstein expanded Planck's idea. He proposed that light itself was made of discrete packets, later called photons. Through his explanation of the photoelectric effect, Einstein showed that when light of a certain frequency strikes a metal surface, electrons are ejected, but only if the photons carry enough energy. This proved that light behaves both like a wave and a particle, an idea that shattered the foundation of classical physics and earned Einstein the Nobel Prize in 1921. Energy was not continuous, it was granular, structured. The universe itself seemed to whisper, "There is a smallest unit to everything." In 1913, Niels Bohr applied the concept of quantization to the atom. He envisioned electrons circling the nucleus in discrete orbits, each with a specific energy level. An electron could jump from one orbit to another only by absorbing or emitting a quantum of energy, a photon. For the first time, this model explained atomic spectra, the bright lines emitted by excited gases when viewed through a prism. Each spectral line was a fingerprint of a quantized energy transition. Bohr's model was elegant and simple, a bridge between the old world and the quantum one. In 1924, Louis de Broglie asked a daring question. If light could behave as a particle, could matter behave as a wave? His hypothesis, that every particle has a wavelength, was soon confirmed by electron diffraction experiments, forever merging the worlds of matter and energy. Building on de Broglie's insight, Erwin Schrödinger formulated his wave equation in 1926, describing how particles evolve as wave functions, oscillations of probability, not certainty. The quantization of energy naturally emerged from the mathematics of these standing waves. And Werner Heisenberg, working independently, built matrix mechanics, emphasizing that we can never know both position and momentum with infinite precision. The uncertainty principle. This was not a limitation of technology, but of nature itself. The world, it seemed, was not deterministic, but probabilistic, ruled by quantized possibilities. Then came Paul Dirac, a brilliant and soft-spoken British physicist who unified quantum mechanics with special relativity. His equations predicted the existence of antimatter, particles identical to electrons but with opposite charge. Dirac's work laid the foundation for quantum field theory, QFT. the idea that particles are simply excitations of underlying fields. Energy is quantized because fields can only oscillate in whole numbered modes, much like a vibrating guitar string. Every particle, every atom, every photon is a note in the symphony of quantized fields. The quantization of energy isn't just a theoretical idea, it powers our modern world. Lasers, for instance, rely on electrons transitioning between quantized energy levels, releasing coherent photons that can cut steel or perform eye surgery. Semiconductors and transistors, the building blocks of every computer and smartphone, function because of quantized electron bands. MRI machines exploit nuclear spin quantization to image soft tissue inside the human body. And in quantum computing, qubits use superposition and quantized states to perform calculations beyond the reach of classical computers. In quantum dots, tiny semiconductor particles only a few nanometers wide, the energy levels of electrons are literally tunable by changing the dot's size. These dots now power next-generation displays and biomedical imaging systems. Quantization has become not just the foundation of physics, but the engine of technology. At its heart, quantization revealed something profound. Nature operates in rhythms, not continuums, in pulses, not waves. Energy comes in finite notes, and our reality emerges from their harmonies. From the glow of the sun to the quantum bits of a supercomputer, everything is built on these discrete steps, packets of potential. The more we look, the more we see. The universe is digital at its core, woven by quantized threads of energy and information. When Planck made his reluctant assumption in 1900, he could not have imagined the world it would open. The quantization of energy didn't just change physics, it changed our perception of existence itself. It taught us that even the smallest leap, one quantum at a time, can transform the universe. If you found this content helpful, don't forget to like this video and subscribe to the channel. Leave me a comment. Let me know what you think about quantum energy and modern technology. Join me next time for another deep dive into the strange and unusual world of quantum physics.